Good afternoon, everybody. Today, I am Suyash. I am from Ribbon Communications. I have with me my colleague Souvik, who is also from Ribbon Communications. And we are collaborating with Red Hat Anita, who is the product manager for networking and NFE. Today, we are here to talk about the best practices from the host level as well as the guest level to achieve maximum performance for a TelcoNFE app. Before starting, just wanted to let you know that earlier this presentation was with Sonos Networks INC, but 8 days back we had a merger with GenBand. Sonos and GenBand together after merger are now as part of rebranding our Ribbon Communications. So as part of this session today, what we are covering is just a brief overview what a session border controller is. We would like to give a background on that. So what are the real-time application needed or requirements of that? And then what are the cloud requirements if we want to put the TelcoNFE app in a public or a private cloud? Then we are talking about various bottlenecks that we need to address to get the maximum performance. Then various optimizations at the guest and host level. Then we have whatever choices that we have for networking based on the type of deployment scenario, whether it's enterprise workload, medium workload, wherein you are catering to a small and medium enterprise versus a carrier-grade deployment. And then we are talking about the roadmap items, couple of blueprints which are coming in future releases, as well as accelerated devices which we need to achieve maximum performance for a TelcoNFE. So just to get started, what is a session border controller? If many of you are aware, right, for a VoIP call, if a caller calls a callee, 2 legs of the call happen to make a single session. So with that session in place, all the operators happen to deploy a session border controller at the edge of their network. The idea behind of putting a session border controller in the edge of a network is to protect the network from various DOS and DDoS capabilities and all that. So just like you have firewall for your enterprise workloads, wherein you're protecting your non-real-time traffic, which is all static rules configured for your applications. Similarly, for real-time media, you require a session border controller, which takes care of various interworkings between your endpoints and all that. So in simple terms, it's Swiss Army knife of a network. It does signaling interworking. As you are traditionally aware, right, each of the endpoints of VoIP used to have separate SIP interworkings or SIP RFCs implemented. Not each endpoint can talk to another because of the proprietary headers and all that. You require an interworking agent in between to make one guy aware of what the other guy is speaking or wants to communicate in terms of the call setup or session setup. Similarly, you need to have media interworking. For each of the operators, if you take up any tier 1, tier 2 operators, each of them have designed the network around a specific codec, bandwidth optimized codec. Or if you come from a PSTN world, folks happen to use G711 codecs and all that. So you require interworking between these two endpoints. Then it also acts as a traffic cop. So whichever session is inactive, you just need to open the pinhole only for that session. Rest all ports you need to block such that your resources are not getting wasted. Then you need to do this congestion and overload handling. Assume that you have a New Year day or some Mother's Day or all that. In those cases, a lot of folks tend to call up. You have a lot of simultaneous sessions, folks making calls via the network. So at that point in time, you have to do some sort of overload protection. You have to reserve the bandwidth for emergency calls or 911 calls such that they go through. Then it also does the traffic inspection, kind of a deep packet inspection of the packet, what the packet is, whether it's a rogue packet, is the stream active or not, all those kind of things. So why is this particular session border controller, a TelcoNFE app, very special? One reason is it is one of the unique apps which is compute, network, and I/O intensive. When you're doing pass-through sessions in which the RTP is just relayed from one endpoint to another, you're doing line rate packet forwarding. So it's a network intensive app. When you're doing transcoding between various codecs, between various operators, or from PSTN to the wireline, or all those kind of things, each has a different codec. You're transcoding between them. So it's a compute intensive app. Along with that, when you're doing large number of sessions, what happens is you have to generate CDR records, logs, and all that. And if lawful interception is enabled, you're tapping all of those calls as well. So you end up doing packet captures and tracing for all those calls. And you're doing that at a very high capacity. So it's an IO intensive app as well. Because of these three special requirements, it requires special tuning to gather the same set of capacity or performance in a cloud as compared to a custom built hardware. So this is a particular use case in which an SBC sits. So as you're aware, right, today the way you're communicating has highly changed. Right from making WhatsApp calls or from Facebook Messenger or the latest release features, Google Alexa or Google Home or Alexa app, from which you can place outbound calls. Each of them have specialized bandwidth optimized codec. And when you're making the calls to PSTN and all that, you require multiple interworkings between them. Consider a landline user making a call to a VoLTE subscriber or voice over Wi-Fi subscriber. All those are involving complex call flows, which requires control plane, signaling messaging, SIP signaling messaging, and then media interworking. And then you require transcoding and transrating. Assume that one endpoint is GSAN learn 10 millisecond packetization time. The other endpoint is GSAN to learn 20 millisecond packetization time. To interwork between them, you require the session border controller to handle all of that. And for lawful interception, for the rogue elements, you handle all of these things as part of the SBCNFE. So if you look at the evolution, traditional evolution of any TelcoNFE app, unless he's a greenfield or developed from scratch, everybody has a custom hardware for which they have a dedicated motherboard in which they select a network processor to do forwarding traffic, line rate, packet forwarding, and all that. Then they have transcoded chips to do audio or video transcoding for a particular session or a stream. Then they have the normal cups or Intel CPUs or any CPUs, generic CPUs to handle your SIP signaling or control plane, which could be SIP or H323. When you evolve to an NFE, the first and foremost goal would be to get it working on a Linux OS or custom-built COTS server. Then you virtualize it. Then the next evolution is towards migrating it to identical instances in cloud, by which you can stamp out each of the instances and scale at a larger or higher rate. So here is one particular unique network traffic packet size. If you compare a TelcoNFE app with normal web-based NFE or anything, right? As you can see from the left-hand side, GSAN learned 29A, 10 millisecond packetization time, the packet payload is 88 bytes. But if you compare a video payload, it's close to 1400 bytes. The audio payload is 15 times smaller than a web payload or a video payload. So when you look at these packet sizes, NFE or a TelcoNFE, real-time TelcoNFE is dealing with smaller packets. So when there are smaller packets, the result is for a 1 gigabyte incoming traffic or an outgoing traffic, you are ending up handling 1.4 million packets per second. But if you similarly look at the video one, it is just 0.1 million, which could be easily handled by even a Linux IP stack. You don't require customized user space, packet processing drivers or anything, or software to process such low amount of traffic. And the reason you have G729A 1.4 millisecond packetization time is the network is fixed, the network is laid out. As a carrier or as an operator, you would like to monetize that network. You would like to get maximum amount of sessions. If you're doing GSAN 11 sessions, you would just end up doing 9,000 concurrent sessions with 1 Gbps of packet ports or the media ports which are handling. But if you do G729AB, you end up getting close to 32K sessions, which is more money or revenue to the operator. Just to summarize, when we look at the web cloud and the telco cloud, web cloud just does packet manipulation or packet handling from layer 5 to layer 7. But if you look at the telco cloud, it does packet manipulation or packet handling from layer 2 to layer 7. Layer 2 is even stripping of the VLANs from one endpoint, addition of the VLANs and all that. The web traffic is all TCP based, connection oriented. The UDP traffic, or rather the media is all based on UDP, RTP, because you require continuous fast processing. Similarly, all the calls are instantaneous in nature. Web is queued. If there are latencies, if an email comes in, it comes at a slightly delayed time, it does not matter to you much. But if a call is made and you don't happen to hear voice for a couple of seconds, you'll just drop down the call. So the way performance tests, this particular slide, I'm talking how the TelcoNFE performance testing is slightly different than the web-based NFE. Here, if you look, we have this Red Hat OpenStack 10 controllers with redundant Ceph storage and the computes, SBCNFE running on the compute node. And then you have this test equipment to pump calls. when compared to web-based appliances or VMs, you just happen to use iPerf tools to do benchmarking or testing. Those are all TCP-based. But when it comes to SBC-NFE, you're doing UDP-based benchmarking, that too at line rate. Packet arriving from your untrusted side or internet side at 1.5 million packets per second, and going to the trusted side, which is your local intranet, at 1.5 million packets per second. Then, what are the performance requirements for the SBC-NFE app? First is guaranteed application response time. Whenever you pick up a phone and you happen to make a call, the network should honor your call. It should not take 5 seconds at one go, 10 seconds at another point in time. Then it should have low latency and jitter. When the audio is being communicated, you should not have delays in your network and all that. Or SBC in turn should not introducing delays and additional things. Then it should be deterministic. With tuned OpenStack parameters and all that, you would have positive impacts on the throughput and capacity. You can get in more number of sessions in the same equipment or in the same VM flavor. You should have 0 packet loss, close to that. Assume that you're making mobile banking, wherein you key in your credit card details and all that. If you had packet loss and all that, whatever key digits are lost, the transaction would never go through. So we should not have any packet loss in the network. So these are the requirements from a TelcoNFE. My colleague Souvik would cover from here what are the performance optimization, the fine-tunings needed at the guest and the host side.
So what we know is now how a TelcoNFE is different from a normal web-based application. And what are the important things which we have to keep in mind when we say we are performing at the best for a telco level NFV. So the major parts, as we've discussed, the telco NFVs are more CPU intensive, network intensive, and IO intensive. So the major things which gives us the problems or the pain points in achieving the performance of a bare metal or a custom-based hardware are the CPU, the memory, the network, and the new addition of hypervisors, which is extra from our custom-based hardwares. So why CPU? CPU is because now with virtualization coming in, CPUs are shared across multiple VNFs running on your compute. Memory, because again, there will be small memory pages, which is by default created by the kernel. So more and more memory intensive work is done, more and more page in, page out will happen, increasing the load on the hypervisor and decreasing your performance. Network, yes, as we said, we are about to handle around 1.5 million PPS. So network has to be at the best with the lowest latency and lowest packet losses. And then, yes, the new hypervisor layer which comes in with the cloud or any virtualization has its own impacts of mapping the instructions, so which in turn has an overhead of computation. So few of the most important points which we have to remember when we talk about performance tuning on a guest level. The first and foremost is when we are virtualizing everything into a single box from a custom hardware, like the network processors which was there, which was taking care of media, then there was the DSP cards which was taking care of transcoding in the custom hardwares are all integrated into a single VNF. So they're all sharing the same x86 cores. So we have to take special care of isolating the type of work each and every core of your VNF is doing. That gives you the optimal performance, and that reduces the interference of O&M traffic to a media traffic, where the O&M traffic can get a little bit delayed, but the media cannot. The next, which is important, is use of the pole mode drivers for network traffic. The interrupt-based drivers, which normally the Linux or any other host guest OS gives, is good till a certain limit, but it won't give you the required performance of 1.5 million PPS. So the only way of achieving is the pole mode drivers, which is given by either DPDK or the Linux Foundation, which comes with the PF ring. Then, as memory is another issue, so use of huge pages gives you a much better performance than the normal memory, where the kernel will again page in and page out the 4K page sizes. And another important thing is doing a proper sizing of the VNFs depending on the workloads which is required. Like if you require a very small number of sessions, it's no point creating a huge VM and hogging the resources where the other VMs will be deprived of. So this is the main or the basic of attaining performance in OpenStack for the telco NFVs. What it says is, let's try to localize as much as possible the CPUs, the networks, the memories into a single socket, or what we call is a single NUMA boundary. So what benefit it gives is the memory access will be faster, the PCI accesses will be faster, the CPUs will be all governing at the same rate, the cache misses reduces, the TLB misses reduces, giving you a better performance. On the other side, if you don't do a pinning and it goes across the NUMA boundary, then the QPI link comes into picture, which adds a basic overhead of any other memory access or network access. So before going into a little more details of what all CPU or memory changes which is required, this is just to give you a brief what performance gains we look at when we have an optimized NFV running and with all the performance changes which is done at the OpenStack level. So if you have huge pages enabled, which is by default disabled in OpenStack, you get around 10% improvement in the latency factors and so on. So the NUMA awareness, the pinnings of CPUs, the CPU mode gives equivalent improvements of performance. Same goes with the calls per second, which is also again very important for any other telco NFV. So you can see with the optimized NFV and with all the optimization in OpenStack, we can gain around 5 to 6 times the calls per second, which with the default settings will be much more lesser. So now just check what are the tunings which is required for the CPU level. So the basic, as I said, we have to localize all our workloads from CPU, memory, and network side. So for that, the first and foremost is obviously, yes, you have to pin your vCPUs to the physical CPUs. So the vCPUs doesn't shift across multiple CPUs, which in turn will give you more cache misses. So to reduce the cache misses, you have to have CPU pinned to the physical cores. The next comes the CPU instructions, because now with the virtualization layer coming into picture, the host level instructions is different from the guest level instructions. So as much as you can expose the host level instructions to the guest, that gives you the maximum performance from the CPU perspective. One more major thing which by default OpenStack has is a 1:16 overcommit from the CPU perspective. So which has to be definitely removed in case of telco NFV, because we cannot have overcommit in CPU in a compute where a telco NFV or the real-time applications are running. Then segregation of real-time and non-real-time workloads. So that will obviously gives you the more benefits of properly utilizing your computes. And isolation of the host processes. So when we have the telco NFVs running on the VM and we have pinned to particular cores, we have to also remember that there has to be some cores left around for the host processes to run. There can be OpenStack processors, there can be so many other processes which are running on the host. So those has to be isolated out. The cores has to be separated for the host level process and the guest level processes. Coming to memory. So as we were all saying that NUMA awareness, yes, that is the most important thing which is required to get maximum out of the memory. Use of use pages. So use of use pages in this is, we have to create use pages at the host level, which has to be used as the complete RAM or the memory for the guest. So that gives you the maximum performance, reducing the number of overheads of the hypervisor. And again, by default, the memory commitment comes as 1:1.5 in OpenStack, which has to be reduced to 1:1. So this is how the CPU and the memory recommendations goes. So for the network part, I'll just hand it over to Anita for the rest of the thing.
So OpenStack has 3 options today for networking. One is the default Open vSwitch option, and this gives you good bandwidth for low performance requirements, and this is your default. There is no CPU pinning for this. And then you can run it, all the switching applications. You have tunneling, you have live migration, and any kind of IGMP snooping. All of those switching applications are available with Open vSwitch. Moving to the next level, which is OVS DPDK. Here you have Open vSwitch accelerated with DPDK, so you are doing a kernel bypass. When you're doing the kernel bypass, yes, you're getting better performance, but you're losing some of the switching capabilities that the kernel has to offer. So you would have limited number of tunneling, VXLAN, and some live migration capability. and some IGMP snooping, but not all the tunneling options and not all the QoS options. And moving to the last one, which is the high performance one, which is SRIOV, and this is a pass-through. You again bypass the kernel. It's a direct pass-through where you're mapping your VNF directly to your NIC with direct memory access. And this one gives you almost bare metal performance, line rate performance for traffic, but all your switching is now moved to your top of rack switch. And this is a overview of what the performance range is roughly that we are recommending on the Linux platform. So you have low range kernel OVS around 50K packets per second. You could probably do higher if you do better tuning, but this is a safe estimate. No tuning on this, default. And if you're looking for mid-range, we're saying 4 million packets per second. This is bidirectional with 64-byte frames. So you're saying 2 million each direction, but this is per socket. That's because OVS DPDK today still does not have all the NUMA awareness that it needs from OpenStack. And then we have SRIOV, which gives you line rate. Performance, you can go 21 million packets per second or higher. And there are performance updates coming in for NUMA awareness coming in Pike. Let's look at SRIOV, which is for your NFE deployment. This is what it would look like if you are doing a deployment with OpenStack today. You have, with the NFE requirements where you have bonding happening, you have multiple NICs tied together in a bond and going to the top of rack switch, either tied to a PF or a VF. And they have, in some cases, bonding over multiple two bonds coming in and to ensure redundancy as well. In these kinds of use cases, you're looking at high performance, line rate, bare metal, and DPDK is being used in your application. So you have, with DPDK moving next, you have a very active loop. That means your DPDK process is running at 100%, tying up the CPU. It's every packet that comes in is being shipped out. In this case, this is an example with 5 vCPUs for the guest. And you can see that we have one interface that is tied to OVS. And this interface is just doing SNMP or other control plane signaling for the VNF. And the rest of them are going SRIOV. What this states is you need, this is the NUMA layout. You have to allocate at least one core, which is 2 hyperthreads. We recommend running hyperthreading because it gives you 30% performance boost. And reserve one core for management and for IRQs for the host. The rest of the cores can be allocated for your VNF. So the overhead for SRIOV is really low. But there is one issue that is going, which is your QEMU emulator thread. And this one needs to be repinned in order to get isolation. Because today, this is a hypervisor thread that can interrupt your vCPUs on your VNF. And we have to, in Pike, you will see that there is enhancements right here for improving the CPU pinning for the QEMU emulator thread. So there is an option with Pike where you can now move it to a separate physical CPU, pCPU, other than the vCPUs that your VNF has. And then with Queens, there's debate going on whether we can actually use some of the, instead of allocating a full vCPU for this, whether we can actually reuse some of the vCPUs that are used for control plane for this QEMU thread as well. And this is the enhancements that's coming in for SRIOV. This is coming with Pike as well. Blueprint is right there. This has been approved. And this is for supporting non-PCI VNFs. Let's look at the use case here. So we have VNF 0 comes in, gets allocated on NUMA node 0. NUMA node 0 has your SRIOV NICs. And VNF 1 comes in, gets allocated on NUMA node 0. VNF 2 comes in, gets allocated on NUMA node 1. And then we have NUMA node 3 comes in, which requires SRIOV, but there's no room on NUMA node 0 because the VNF 1 that did not require SRIOV got balanced on that NUMA node 0. So what is coming in Pike is some kind of PCI layer where you can actually say that all VNFs that don't require PCI or PCI device allocation should be allocated on NUMA nodes that don't have PCI devices as a preference. So then you would have the correct allocation when, so NUMA node 0 only has the VNFs that have SRIOV. Moving to OVS DPDK. With OVS DPDK, this is a typical layout with OpenStack today. All of your, you have DPDK ports on the bottom. These are the data ports. And you also have your signaling and control plane going through DPDK NICs on the left-hand side as well. And on top, you have regular NICs for OpenStack API, and you have NICs for install purposes. So this enables you to have live migration, and there are enhancements going in for that, as well as VXLAN east-west tunneling. And your bonding is now done by your OVS DPDK vSwitch. When you're doing CPU pinning and partitioning with OVS DPDK, there is an additional step. In addition to allocating CPUs for the host, for IRQs, you also have to allocate CPUs per NUMA node for your OVS DPDK. So what we're saying is you need to allocate at least one PMD thread or vCPU per queue or per port. If you're running MultiQueue, you may have more CPUs that need to be allocated. If you have one port, and running single queue, one PMD thread is all you need. And we're also saying that OVS DPDK is not yet NUMA ready. And if you're running cross NUMA, then you're going to see at least a 50% hit in your performance. And what we mean by this is there is a discussion going on upstream where, and the design is under discussion, but this is the basic issue where a VNF needs to be allocated on a NUMA node that has the DPDK ports. But NOVA is unaware of which NUMA node has the DPDK ports and needs Neutron to provide this information on which are the DPDK ports, because it's not a PCI device anymore like SRIOV. It's hidden behind a vSwitch. And then it needs this extra bit of metadata from Neutron telling it where to allocate or where to put the PMD threads and the vCPUs needed for this VNF on the right NUMA node. And this is an example of testing that we did in-house. This is not a typical, this is not a OpenStack layout, but this is an OpenFlow pipeline, which is very simplistic, only 4 rules. But what we've done is we've put the VNF on a different NUMA node, and the DPDK ports on a different NUMA node, and you can see the performance hit is roughly 50%. If you're running for smaller packets, if you're running larger 1500 byte packets, you won't see that much of a performance hit. Let's look at MultiQueue. MultiQueue is something that can give you additional performance, and a lot of VNFs are now designing for MultiQueue. So with MultiQueue, what that means is it's a flow-based steering. So you need to have, and a flow is identified by a 5-tuple. It could be IP addresses, source MAC, destination MAC, VLANs, UDP, TCP ports, to identify a flow. And based on those flows coming in through your NIC, you use receive-side scaling, which most NICs support today. And if you have MultiQueue enabled, it will allocate to different CPUs automatically. We recommend one CPU per queue, ideally. And if you have multiple queues and you put them on the same CPU, it's not recommended for NFE real-time applications, but you could do it if you have unused queues or if you have very lightly loaded queues. And this is an example of a NIC with 4 queues. And we recommend 4 PMD threads, which is 2 cores and 4 hyperthreads to support 4 queues. What we want to do is have all the PMD threads or the vCPUs equally loaded. You might run into cases where traffic is not equally loaded, and that comes when either you don't have enough flows or you have flows that are, certain flows are heavier, the load is heavier on some of them, or you have an active backup link and one port is not being used at all and you have no packets on that. So there is work in progress on Open vSwitch to do auto rebalance of queues to detect and when what the queue level load is and to be rebalanced between the vCPUs, of course with zero loss. And that's all work in progress. So in OpenStack, when you do multi-queuing, you have typically 1 queue per VM CPU. So in the example that we had earlier, we have a guest with 5 vCPUs. In this case, there are 2 Ethernet ports, virtual Ethernet ports, ETH0 and ETH1. And ETH0 on the left has only 1 queue being used because it's control plane only. And ETH1 on the right has 4 queues, so 1 is unused. So 1 queue is being unused in this, and so you have, in this case, is an example of having unused queues, and you would like to auto balance and not have a vCPU dedicated for these unused queues. But MultiQueue does have a performance bump, and you can see that you have a linear performance increase as you add more PMD threads and as you add more queues and vCPUs to OVS DPDK, similarly for Open vSwitch. I'll hand off to Sue.
So just to sum up the last slide, what Anita was saying about the MultiQueue. So MultiQueue is, yes, OVS DPDK definitely has a performance boost when we use MultiQueue, and it is almost linear. So this is one of the performance data which we have, where we have used MultiQueue with not OVS DPDK, but with OVS. And the results are almost similar as we got in OVS DPDK also. Almost similar doesn't mean 4 million PPS, which was shown, but the linearity. So if you see, without any other performance improvements, the basic default settings, we were getting around 350 active calls with quite a bit of high packet losses. So with MultiQueue with MultiQueue enabled, if you see, the packet loss goes down massively. The session count is almost 4 times. So we can see from here that OVS or OVS DPDK both has got equal benefits when we have MultiQueues enabled on the host layer. So for any other future things, I'll just hand it over to Suesh.
So when you're doing line rate packet forwarding, wherein the call comes in, you are just changing the source and destination IP, source port and destination port between the 2 endpoints. Your custom CPU is good enough. It can do close to 1 gig or 10 gig line rate handling. But when you're doing transcoding, when you're changing the speech codec of one format to another, we recommend usage of accelerated devices. So if you look at the public clouds, Amazon and all that, already there is FPGA, F1 instances and GPU-based instances available. So one of the telco use case or NFE use cases, wherever there is transcoding required, we could leverage the use of GPU. It's already used in multiple other streams like AI, machine learning, Bitcoin operation for cryptographic manipulation handling and all that. We could use the same thing for audio transcoding as well. And if you look at the power levels or power consumption levels between each of the available solutions like custom hardware and all that, it's only in a binary mode. Assume that I'm using a custom hardware to support 10,000 transcode sessions. If I require an additional 500, I have no other choice to but buy a complete new custom hardware box because there is no scaling or elasticity available, or only one option is keep on adding the PCI chipsets till the motherboard or the hardware can support. CPU-based transcoding is another alternative, but with the CPU-based transcoding, the issue is you cannot get infinite scale, or you would not be able to scale as high as what you could do with custom hardware, but which comes at additional cost. So the third alternative is GPU transcoding. So GPU provides you additional cores and the scale is pretty high. The growth is pretty high. When compared, it gives comparable performance as that of a custom hardware. Also, if you look at as a data center operator, right, power utilization levels are pretty important for you. GPU takes up quite low powers compared to custom hardware which is getting used. As part of our proof of concept, we are able to do transcoding with NVIDIA M60 GPU between each of these various codecs, wideband, EVRC, G722, and all that. Work is in progress to support additional Opus or Silk-based codec, which are used for Google Talk and WhatsApp and all that. So GPU is one recommendation for the usage of accelerated devices for TelcoNFEs. The other recommendation is use of smart NICs. Like there are quite a lot of options available in the market like Mellanox, Metronome-based NICs, wherein you could offload some of your packet processing capabilities onto the NIC, like UDP checksum calculation and all those kind of things, which would greatly reduce the overhead or the CPU utilization level that the guest takes up. We spoke mostly about all of the blueprints. Anita has covered the list of blueprints which are coming in various OpenStack releases, which would further help a TelcoNFE app running in OpenStack environment. So this concludes our presentation, and we could have Q&A.
She wants to go back one.
Okay.
Yeah.
I have seen that for your obvious DPDK, you have in the CPU which is performing the soft switching things. So if I have a database server, you also need high I/O on the network side. You also need high performance on the database processing and stuff like that. So do you recommend to add more CPU just to process the database thing to do things, or we can share those CPU for the database processing?
You're talking about sharing the CPUs which are allocated for the PMDs of the DPDK?
Yeah.
Okay, so from the recommendation perspective, I think we don't recommend reusing or sharing the CPUs which are given for the DPDK PMDs on the host. They should be, and you cannot directly share because as Anita was saying, they're running in an active while loop. So it's always busy loop which is running on those CPUs, so those CPUs cannot be directly shared with any other processors.
So you will see, you can try it out if you are, but you will see a performance hit, and you probably will see loss on your, if you're putting your same vCPUs for DPDK as well as for a database processing.
So basically you're pinning the things on the host level, not the guest level.
We're doing both.
Both.
So the VNF is being pinned, and then at the guest level, for SRIOV, you're just doing VNF pinning. But for OVS DPDK, you're also doing OVS PMD thread pinning in addition on the host.
And just to add to Anita and Sauvik's point, right, if you happen to share that same core for the DPDK thread as well as other process, then there is process contention and switching, which in turn will add additional issues to your scheduling and all that.
Any other questions, comments?
Yes.
I think in one of your slides earlier you mentioned CPU pinning or something like it, but pinning CPUs related to the task they were performing. So I think it was like data plane pinning and control plane pinning.
So, yeah. So if you look at any application, right, there is some portion to it which is doing real-time media handling. And then there are O&M tasks like querying of the alarms, SNMP related stuff, OM and all that, wherein you are doing non-real-time work. Like for the call, you are trying to look at the logs and all those. The process which is doing logging or the process in which you are reading some stats and all that, that should not interfere with your media handling course. So we would require all non-media handling tasks or processes to be pinned to a particular core. That way, no process switching or anything occurs, and you don't end up adding latencies and delays to your packet flows.
So they're different. Are they different VMs?
Same VM, in that you do the core segregation by either using C groups, C sets, or
Okay, so there is a way to do that.
yeah.
Internally.
I think we have 1 more minute. Any other questions? Thank you.
Thank you.
Thank you.